Hello, this is Alexandre Arnoult from l'ICMBE21 Toulouse, France, and I will introduce you today a new tool that we have developed in the lab, which allows to measure the curvature in real time and in situ in an MBE environment, primarily developed for this, but which can be used in any other environment, and which we named Magnification Inferred Curvature. And I will show you how its measurement can be applied to the study of the growth of dilute bismide. This work was done with Jonathan Collin, who developed with me the tool, and with Clara Corny and Chantal Fontaine, with whom we studied the growth of dilute bismide. So first, I will speak about this global approach we have in the lab, that is to use many different in situ diagnostic tools to better understand and further control the growth. Then I will focus on this curvature measurement tool and show you with a few examples its capabilities. Then I will show you how this tool helped us to better understand the growth of this quite particular alloy, which is gallium arsenic bismuth. And then I will conclude. During a growth, there are many different processes that will occur, and many will change during the time. What you can do after the growth to understand what's been going on is to do some ex situ measurement like X-ray diffraction or ICM, but this will just be an autopsy of your growth. I mean, you won't get access to every dynamic process with it. So our approach is to use many different in situ and real-time diagnostic tools to monitor different parameters during the growth, like stress, reflectivity, surface morphology. We can also monitor the fluxes during the growth and use this parameter to understand first what's going on, and then to act to the growth, to change the growth itself. Of course, there is no perfect diagnostic tool that will give you a complete picture of the growth process. So the best is to couple many different tools to maximize their complementarity. So this is what we do. So this is one MBE chamber. It's an MBE 412 chamber. 4 stands for 4-inch wafers, up to 4-inch wafers, and 12 stands for 12 effusion cells. In this MBE machine, we have a spectral reflectivity with a white light source and a CCD spectrometer. We monitor the temperature with a KSA bandit, which allows us to follow the band gap of the material and infer the temperature out of it. We constantly measure the fluxes with an atomic absorption tool. We use a read also in this machine constantly, even if the sample is rotating, as the read tool is synchronized to rotation. And during synchronization, we can access to in-plane lattice parameter and Strix intensity. I will show you this tool by the end of the talk. We have developed a roughness tool which is based on diffuse light scattering. You see here a perfect wafer and here a diffusive wafer where the surface is obviously rough. And finally, this curvature measurement tool, which I will speak about mostly during this talk. All these tools are synchronized to rotation. They are all acquiring the data in the same time base, and they are all linked to the MBE control software, so that we can use their complementarity. This is a geometric configuration in this chamber. So the flux are coming from below, and the wafer is held by its own gravity by a molybdenum block. There is no clamping of the wafer, so the wafer is free to move, which is compulsory if you want to monitor the curvature. And finally, for all what I will show you today, the wafers are rotating around their axis. The physical parameter we're interested in is not curvature, but stress, but both are linked. Usually, there are 3 stress components which are distinguished. First, the thermal stress, which comes from the difference in expansion coefficient between film and substrate. Then the intrinsic stress, which is a stress source which we introduce during the MBE process. It comes from the lattice mismatch, from growth relaxation, surface or interface stress, incorporation or desorption of impurities, phase transformation, and so on. And finally, there is extrinsic stress, which is a stress that can be induced by external factor, like external loading or exposure to environment, and we try to avoid this extrinsic stress during the growth. Rapidly, a few definitions. So stress is a force per unit area, and I will speak about incremental stress, which is a product of the stress and the thickness of the film, which unit will be in Newton per meter or gigapascal times nanometers. For thin films, the presence of the free surface sets that the stress generated in the layer is biaxial. That means that it's in the plane of the film. And finally, if the substrate is sufficiently thin, it can curve as a result of stress in the layer. And then we'll speak about curvature, which is 1 over the radius of curvature. So why are films usually in a stress state? This mainly comes from a lattice mismatch between a film and substrate. If the lattice parameter of the film is smaller than the one of the substrate, then the film will end up in a tensile state. And if the film has a larger lattice parameter than the one of the substrate, then it will end in a compressive state. By convention, I will use a positive radii of curvature or positive curvature for tensile stress and negative curvature for compressive state. So you will have a bending of the whole system film plus substrate, which will end up in an equilibrium state, and you can define a radius of curvature of this system. The Stoney equation, which Stoney developed in 1909, so it's not very new, sets that the curvature, or 1 over this radius of curvature, equals 6 times the stress in the film times the film thickness, and divided by the biaxial modulus of the substrate and the thickness of the substrate to the square. This Stoney equation is valid, provided some assumptions here. The most important ones for us being that the biaxial stress of film or substrate are the same, and that the film thickness is significantly smaller than the substrate thickness. If this is not the case, then you can use this correction factor, but in all what I will show you today, this correction factor is very close to 1. So we'll just use the simplified Stoney equation. So how can you measure this curvature during a deposition process? There are two ways. So the main way is to use laser deflection, which has been used for years now. And so we propose this new way by using the measurement of the magnification of a virtual image. First, how this was done historically. Consider laser beams and use a matrix of parallel laser beams. If you shine this matrix to your wafer, then the reflective beams will be deviated by the substrate, so this is diffractometry, and you will have some spots, laser spots that you can detect with the CCD detector, and if you measure the distance between the spots, you can deduce the curvature out of this distance. There are many different labs which have been using this technique, and you can also buy tools from different companies to use this technique. So why not just using laser diffractometry? It's commercially available, it's widely used in the sputter metal thin film academic community, but in very peculiar conditions. They use very thin substrates and they don't rotate during growth. It's also used in the MBE community, but only on the gallium nitride materials, because they are highly strained, and so high stress means high curvatures. It's also widely used in the gallium nitride LED MOCVD growth industry. There are advantages with this technique. It's a proven technology and it's quite robust to vibrations because you measure relative spacings between the spots. But there are also some issues. The first and main one for me is that it's very sensitive to misalignment. You need to align the system before each experiment and even during long experiments. Then you need to use motorized motors to always tune and to capture these spots with a CCD detector. It works only at normal incidence, and there is also another main issue, that is that you use monochromatic light with lasers, and if the reflectivity of your sample is changing a lot, like when you're growing bright mirrors for instance, then you may lose your spots from time to time. In order to overcome these issues, we developed in the lab another solution which is based on the measurement of the magnification of the virtual image, so it's completely different physical phenomenon. So this is the principle of this technique. Consider an object here and the sample here with its surface which will act as a mirror, and then this mirror will create a virtual image of the object. The size and position of the virtual image will depend on the curvature of the sample, and you can acquire this virtual image with a camera and a lens. Now you can compare the size of the object to the size it will have with a flat surface here, and then you measure magnification factor from which you deduce curvatures. The main advantage of this technique is that it's highly stable and alignment free. You just need to align it once when you install the system, and it's okay. The object is made of a plate with holes drilled on it on a white light source. So this will create white light spots, and you capture with a camera the virtual image of these spots, from which you can measure the position and then the distance between the spots. Here you can see one of the geometric configuration of the system. There is a white light source with a plate here with holes on it, so this is the object, and here you've got a camera with its lens, and they are looking at the wafer at normal incidence. We are dealing with spherical mirrors, so this is well known, and you can find in any textbook that the magnification factor of a spherical mirror depends on the distance between the object and the pole of the mirror, and depend also on the radius of the mirror. So you can deduce from this, of course, the curvature as a function of the other parameter, and so as a function of this magnification factor. But the virtual image is not always at the same position, and you capture a projection of this virtual image with the camera on its lens. So you don't measure the actual magnification factor, but a modified magnification factor, which I name here gamma C, which is the one seen by the camera. And so you need to apply this correction factor to the formula in order to get to extract the curvature in this configuration. This is another configuration in which you can use this tool. So now it's a tilted configuration where there is an angle theta here. There are two planes, the sagittal and tangential plane, and you will have to apply correction factors, which is 1 over cos theta if you measure your corrected magnification in the tangential direction, or cos theta if you measure this camera magnification in the sagittal direction. In order to validate the set of analytical equations, we created a numerical model of our system, here in tilted configuration at 70 degrees, with the Zemax Optic Studio software. In this model, we can also set the curvature of a spherical mirror here, which is set to 10 meters, and which will simulate the wafer. The object is here made of a 5 by 5 matrix of source points, and the camera and its lens are simulated by a diaphragm plus a plane lens on a virtual detector. It's a ray tracing software, so we can simulate images detected by this virtual detector, which you can see here, from which we can measure the position of the spots. So we can deduce the distance of the spots in both tangential and sagittal directions. If we compare this image with the image also simulated with this software, but with an infinite radius of curvature, that is with a flat surface, we can deduce from these spot distances magnification factors, which we can introduce in the set of analytical equations, and from which we can deduce the curvature or the radius of curvature, and we find back the curvature very precisely, the radius that we set in the system. We did some simulations in various geometric configuration. We changed the angle theta or the radius of curvature, so the angle theta is here. And you can see here a plot of the magnification captured by the camera as a function of theta for different radius of curvature. And the lines are the analytical model, plane lines for sagittal direction and dashed lines for tangential direction. And the dots are extracted from the analysis of these images, which were simulated by Zemax, so the numerical model. And we found less than 0.02% difference between the curvature introduced in the model and the curvature extracted from these simulated images, thanks to our image analysis software and inferred with the analytical equations. There is an interesting feature that comes out of all these calculations, and that is worth noticing. If you consider gamma c, the magnification factor captured by the camera, it is directly derived from the measurement of the distances between the spots. The bigger gamma c, the better the sensitivity for same radius of curvature. You see here that, for instance, for a radius of 10 meters, so that you get this value of gamma c at theta equals 0, so at normal incidence, and that when you increase theta, gamma c increases in the sagittal direction, whereas it decreases towards 1 in the tangential direction. That means that in the tilted configuration, increasing the theta angle increases the sensitivity of the measurement in the sagittal direction. That's what we did, and for the rest of the talk, the measurements were done at theta equal 70 degrees, which gives us an extra 2.9 increase in sensitivity. So now, if you look at these sensitivity results we obtain with this system, so on a vibration-free environment, so you see that at normal incidence, the sensitivity obtained is larger than the one we get in the sagittal direction when we are in the tilted configuration. Whereas in the tangential direction, the sensitivity is worse than the one we get at normal incidence. So to get a higher sensitivity, it's better to use this tool in the tilted configuration and to look just at the data acquired in the sagittal direction. So now let's have a look at some experimental results we obtained with Magnification Inferred Curvature tool. They were all obtained in our 3.5 ICMBE21 gross chamber in the tilted configuration, like in here, and the tilt angle was 70 degrees for all these experiments. First, we can measure the curvature of a bare wafer inside the chamber. So this is a standard 2-inch wafer rotating at 12 RPM and measured at gross temperature. And what you can see is that the shape of the wafer is not flat, but this will be the starting surface from which we will begin the deposition, and then we will add a spherical deformation to this. So we will consider this as a starting surface. The first example I want to show you is the curvature change you will see when you grow some aluminum gallium arsenide. As you know, the lattice mismatch between aluminum arsenide and gallium arsenide is quite low, and it's even lower at gross temperature because of different thermal expansion coefficients. Here at gross temperature, the lattice mismatch is only 0.046%. And this is what you get. So you've got here the thin thickness, and here the curvature, which is proportional to the incremental stress. And when you grow then gallium arsenide on this gallium arsenide wafer, then there is no lattice mismatch. so the curvature is not changing. And as soon as you open the aluminum cell, then you introduce some stress, and as the curvature is proportional to the stress on the film thickness, the stress is a constant here, so the curvature will change constantly with the film thickness. And from the slope you can extract, of course, the stress in the film and then its alloy content. You can do this also in a more complex structure. So this is a gas complete VCSEL structure grown on a 4-inch wafer. So 4-inch wafer means that it's also thicker. It's a 650 micron thick wafer. But anyhow, what you can see here is a trace that you get for the first bright mirror. Then you got the quantum wells here, second bright mirror, contact layer, top bright mirror. Then it's a VCSEL with a modulator on top of it. So these are the quantum wells for modulation, and then the top bright mirror. We can zoom on this area, and what we can see is that there is a small stress during the growth of the doped gallium arsenide, and this small stress is coming from the dopant. So yes, we can see the dopants with this technique. And you can also see here that it's not completely, the slope is not completely constant. There is here the slope is a bit higher, and this comes from the fact that there is a slow flux transient in our MBE machine. We knew this because we also measured it in a flux gauge, and we could also measure it here in live during the growth of the VCSEL. We can also follow the growth of very thin layers like indium gallium arsenide quantum wells. Here we change the indium cell temperature, so we could change the indium content of these 3 different quantum wells, and we see very nicely the slopes which are different and coherent with indium content that was inserted in the quantum wells. So we could directly extract the indium content of the quantum well out of this measurement. Another interesting parameter you can access to with curvature is plastic relaxation. Here we grew a tunnel junction for solar cell, so still on gallium arsenide. So gallium arsenide on gallium arsenide, there is no curvature change. Then here a stress layer with indium, 12% indium, so there is a constant slope. Another layer with 12% antimony, so also another constant slope. But before the end of the layer of antimony, you got here this change in the slope, which comes from the plastic relaxation. Another hint that this is plastic relaxation is that when now we grow gallium arsenide on top of these layers, gallium arsenide is in tensile stress. We can also use this curvature measurement tool to lattice match or control the lattice matching of thick alloys to the substrate. So in this example, we align the lattice parameter of this quaternary alloy to gallium arsenide. This is for solar cells, so for the 1 eV subcell of a multi-junction solar cell. What you can see here, so in green, is a curvature during as a function of time, and here in pink is one of the parameters of the plasma cell, which is a valve in front of the nitrogen plasma cell, which allows us to modulate the content of nitrogen inside the layer. And you see that when we could tune the lattice parameter quite nicely, so this is very small curvature here, and we could tune this lattice parameter by changing this parameter of the nitrogen plasma cell. This was done by hand, but it is also possible to do it automatically. In this example, we grew indium gallium arsenide on top of indium phosphide. So you see here still in green the curvature of this indium gallium arsenide alloy on indium phosphide, and we're aiming a lattice match. And here in red you see the temperature of the indium cell, which was linked to the curvature through a PID loop. And so all this was automatic, and the growth was performed at 500 Celsius, and so we had a perfect lattice match at growth temperature. But then we lowered the temperature to remove the wafer, and what we noticed is that there was a change in the curvature during the cool down, and this comes from the thermal stress. If you look at the X-ray of this structure, you can see two clear peaks, the peak coming from the indium gallium arsenide and the peak coming from the indium phosphide substrate. So we are facing an issue, which is that thermal expansion coefficients are not the same for gallium indium arsenide and indium phosphide, and this thermal stress makes that at room temperature the structure, the lattice parameters are not aligned anymore. We were in this configuration. So here is the lattice parameter of indium phosphide, and here in red the lattice parameter of indium gallium arsenide. And so we aimed a lattice match here at growth temperature, and so we were not matched at room temperature. The strategy to have a perfect alignment at room temperature is then to look at misalignment, to grow gallium indium arsenide in a compressive state to compensate the change in lattice parameter when we will cool down the sample. That's what we did here. So we controlled the temperature of the indium cell not to get a flat, so no change in curvature, but a constant change in curvature, so a constant stress. And then when we cooled down the wafer, you see that curvature comes back to the curvature the wafer had at the beginning. If you look now at the X-ray diffraction pattern of this growth, then now the peak of the indium phosphide is at the same position than the one of the indium gallium arsenide at room temperature. So we could match the indium gallium arsenide layer to the substrate by compensating the thermal stress. So to summarize with this technique, there are many advantages to use it. First, it's very easy to install and it's alignment free. You don't have to do any tricky alignment before each experiment. It's a plug and play system. It's very robust to the wobbling of the wafer, so you can use it continuously while the substrate is rotating, which means that you can access to the anisotropy. It's also almost insensitive to the change in reflectivity of the sample. Because you're using white light and not a monochromatic light, then we can use this system even if we grow brine mirrors, for instance. It's quite robust to vibrations because we measure relative spacings between spots. And it's also very sensitive to curvature. We can study very low mismatch systems. So this system is really suited for MBE, and we use it for every growth, and as I told you, it's a plug and play system. We patented this system and transferred it to Reaper, so it's now commercially available as the EasyCurve tool, which is made of a white light source and camera and its electronics, and with a dedicated software. So let's now have a look at how curvature helped us to better understand the growth of gallium arsenide bismuth. Gallium arsenide and gallium bismuth have a very different lattice parameter. The two binary compounds have a mismatch of about 12%. So it's very difficult to introduce bismuth in gallium arsenide. Anyhow, this alloy is studied for a wide range of applications. There are too many growth regimes for the bismuth incorporation in gallium arsenide. So under 400 Celsius roughly, the bismuth incorporates into gallium arsenide, provided that the 5/3 ratio is about 1, and that you control very nicely, very accurately the substrate temperature. And any small change in these growth conditions will induce a high difference in bismuth composition in your layer. The other regime is above 400 Celsius, where bismuth acts as a surfactant. So in this study, we will concentrate on this range of temperature, so at low temperature when bismuth incorporates in gallium arsenide. And you see here what you can observe while you grow a layer of gallium arsenic bismuth on top of gallium arsenide, so on the standard 2-inch wafer. So you can see here the curvature or incremental stress as a function of film thickness. So still, when you grow gallium arsenide on gallium arsenide, there is no change in lattice parameters, so the curvature is not changing. And afterwards, when you grow gallium arsenic bismuth, what we expected is to have a constant slope, and what you can see is that there are many different features appearing here. There is here some feature appearing at the middle of this growth, and you see that the two slopes seem to be different. So let's have a look at. At the beginning here, if you zoom here, what you see is that the slope is not going down just when you open the bismuth cell. There is a little delay in the incorporation. There seems to be a little delay in the incorporation of bismuth, and this is a signature of bismuth segregation that has already been seen by TEM, for instance, but this is the first time we could see it live during the growth. Now this transition here, if you measure the read during this growth, what you see is that before this point, the surface reconstruction is 1/3, and just after this point, the surface reconstruction switches to 2/1. So here there is a change in surface reconstruction between these two regions. That we can see that there is a change also in the curvature. And now, as we noticed already, there are two different slopes. If you derivate this signal, you will here you have two different plateaus that you can attribute to two different stresses, so two different bismuth contents. So from the curvature data, we can deduce two different concentrations here, so that there are two layers with different concentrations and different thickness also. We can deduce the relative thickness of these two layers because we know the transition between the two. Then we did some high resolution X-ray diffraction on this layer around the O4 peak. You can see here the peak coming from the gallium arsenide substrate, and here all these patterns coming from the gallium arsenic bismuth. We did some simulation. You can see here in blue the simulation to fit the diffractogram in black, and this is what the simulation gives on the end of the fit. And you see that there is a very nice correlation between the X-ray diffraction in terms of thicknesses and also in terms of bismuth content when you compare X-ray diffraction and curvature. To further study this transition that seems to occur during the growth of this alloy, we used a trick, that is to use a very thin wafer. We did the same growth on a gallium arsenide 100 micron thick wafer, so this is the thinner we can get. And from the Stoney equation, we know that then we got a gain of resolution of more than times 5. And so during this growth on this very thin wafer, we still see, so here we see that there is this delay, so the bismuth segregation, a first slope, then a huge transition, signature, and then a second slope here. We see here that at the beginning then the slope is steeper, so that means that there are more bismuth incorporating in this regime, and then the slope here is less steep, and then there is less bismuth incorporating in this region. So as I told you at the beginning of this talk, we can extract some very useful information from the read, even if the wafer is rotating around its axis. And to do that, we acquire images which are synchronized to the rotation. That is, that we take images only when the crystal is well aligned in some particular directions. And out of these images, we can see the principal streaks and the streaks coming from reconstruction. So we can follow the distance between the principal streaks and extract from this the in-plane parameter and follow the intensity of the different streaks. So this is what we obtain. This is in-plane lattice parameter deduced from these images during this growth sequence when we grew gallium arsenic bismuth here. And this is here the read intensity of some streaks. Here in blue, the streak corresponding to the by 2 reconstruction, and here in red, the streak corresponding to the by 3 reconstruction. Now we can compare what we obtain with the different tools because they are all acquired in the same time base, and you can see here at this transition that you've got a change in the surface lattice parameter, and the change in the surface reconstruction also occurs exactly at the same time. We can even go further and record the thermocouple temperature during this growth sequence. Here you've got an increase of the temperature of the substrate due to the opening of the gallium and bismuth cell. But what is interesting is here the small drop in the thermocouple temperature coming exactly when we got this transition here. So it looks like a phase change. We could also follow the banded temperature during this growth sequence. So this is at low temperature, so the signal is quite noisy, but still we can see that there are some features which are interesting. When we begin the growth of gallium arsenic bismuth, we see an increase of the temperature read by banded, which is not the actual temperature. It's because of the band gap which is changing. And just when we add here this transition, we see that the temperature seen by banded is increased a lot. So the band gap of the material changed a lot also. So what we can deduce from all this is that by coupling different techniques and acquiring data in the same time base, we can better understand, we have access to different phenomena occurring at the same time, and then it's easier to understand the growth mechanisms out of it. So I will conclude my talk. First, when facing peculiar dynamic conditions, I think that I've shown you that in-situ analysis tools are mandatory, and that curvature measurement provides extremely rich information, and that this new magnification inferred curvature tool makes it accessible to MBE. Finally, coupling in-situ tools helps us to further understand the growth mechanism and to control the growth properties of epitaxial materials and further of device structures. I thank you for your attention.